If we look at the gas mass and stellar mass of our halos, we see that they're in agreement with the alfalfa survey generally, but this is the total gas fraction of these dwarfs, and we haven't looked at the temperature dependence of these dwarfs. So it'd be great to look and see if we just select for cold gas, what it looks like, how low our gas fractions go down then. But once again, we see that these dwarf galaxies are looking pretty good with all the observations we're able to compare against at this point, which is promising, but we still need to do more analysis. So the most exciting thing, I think, is the star formation histories of our dwarf galaxies. So if we look at the star formation histories of all the dwarfs around a single vela, we can make a plot of the range of star formation histories, which is this gray curve. So that's the range of all the star formation histories for all the satellites of a single host galaxy in this mass bin. So I've selected them into different mass bins, and then you can see the black line is the average of all those star formation histories. And we can compare them with observations from local group dwarfs. So here I've plotted some of Dan Wise's observations of the cumulative star formation histories of dwarf galaxies in blue. And you can see that at various mass bins for this vela, and this is representative of all the velas, this is just the first one. So I put those plots up here. You can see that we're in agreement with the average observed star formation histories of galaxies in the local group. But we also find a huge amount of scatter, right? This gray area is enormous. So we also find that there is a wide variety of star formation histories in our dwarf galaxies. So in order to compare with all of the velas, since I have here only a single host, what I'm going to show you is this black line, which is the average for all the dwarfs around a single host galaxy. And I'm going to show you all of the averages for all 10 velas. So once again, we're in a single mass bin. So these are all subhalos of a primary galaxy in this mass bin, and all field galaxies, where field is just outside our sphere, of a single mass bin. And we have each line, so all the gray lines, there are 10 of them. That's one for each host halo. So if we look at the star formation history, I was a little surprised that the differences between just radiation pressure and including this photoionization model don't look so dramatic, but this is just the first mass bin. So we notice one other thing that I find interesting is that in the field, our galaxies have built up their stellar mass extremely quickly, even faster than the subhalos. So we see that at 13 gigayears, so we have 90% of the mass is built up already for these field galaxies. And if we step up in stellar mass, we can see that the field hasn't changed that much. Maybe the tail end of the star formation history is a little bit more extended. But our subhalos are starting to look a lot smoother, and the black line is just the average of all these gray lines. So you can see we still have a huge range of differences in the individual star formation histories of the galaxies. But on average, there's some trends where it's looking good, and all of these lines compare very well with the data provided by Dan Wise, but it just would get really overcrowded if I included all the lines. So in these larger objects, we see a much smoother star formation history beginning to develop. This is a little bit interesting here. This seems to be the first by eye difference you can really distinguish between the two models are in the field. And for our largest, most massive galaxies, they have almost a constant accumulation of stars over their history. So it's a continuous buildup of stars up to redshift 1. And it looks like, although there is still a large range in variation in the star formation histories of each galaxy, it looks like they're agreeing with the main trends of observations. So one thing we can look at, which is something that Danielle and I were just talking about this week, is how can we more quantitatively look at the differences between these galaxies. So these different subhalos, what we can do is we can take a single vela, so we can take one host halo from just the radiation pressure one, and divide the two different feedback models. So we can say, if we look at the cumulative star formation history for one host galaxy, and if we divide the model with radiation pressure and photoionization, by the one with just radiation pressure, we can look at how the star formation histories have changed with time. So this is just for subhalos I'm showing you here. And so this is some way we can figure out what's actually happening that's different between these feedback models. So in each stellar mass bin, you can see that the ratio of the star formation histories for each of the host halos, you can see that there's a lot of difference at early times, and it quiets down towards later times. And as you go step up in stellar mass, we see that there is a larger change in later times in the galaxy's history. And for the largest mass galaxies, it looks like there's actually a difference in the star formation histories between just the pure photoheating and the radiation pressure model. So that these are these two lines, up here, the subhalos. So it actually looks like there's some differences between the most massive subhalos when you choose which feedback model you use. So this is pretty interesting, and we would love to do this at redshift 0. So we have created some new initial conditions, and so we just created some new initial conditions, and we're calling these the VLA4s. So we're having, both of us are going to be running it over the next year. We've already run 3 sets of galaxies down to redshift 0. This includes all of the physics I've talked about earlier, supernovae, radiation pressure, and photoionization. And we've included a deterministic model for star formation instead of a probabilistic model for star formation. These are all from the same box of 100 megaparsecs on the side with a resolution of 60 parsecs. So, and we've once again not selected for any specific environment. And so some of these have some major mergers at the end, and we'll be hopefully running about 50 of these galaxies. Right now, 3 are to redshift 0. And so here's a nice image of what it looks like at redshift 3. And so you can see there's a lot of structure. This is a gas density projection of one megaparsec on the side. So there's a lot of stuff going on, and it's going to be really exciting to start looking at these new simulations so we can look at the population of dwarf galaxies at redshift 0. So in conclusion, we've talked a lot about the Vela simulations at this conference, but we haven't yet talked about the dwarf satellite population around these galaxies. Now I've shown you a little bit about their star formation histories, about the abundance of these satellites that we have at redshift 1. It looks like models of radiation pressure and radiation pressure plus photoionization produce similar looking dwarf galaxy populations. Maybe the biggest difference is the abundance of low mass satellites, of low mass luminous satellites, and there's possibly some differences in the early star formation histories of these dwarf galaxies. So we still find a huge spread in stellar mass to halo mass relationship, and I'd really like to look at that more because this has implications for scattering in the abundance matching relationships, which I'm sure Shay will talk about in, I guess, an hour or two. So this is pretty exciting, and we're glad to be running new simulations down to redshift 0. Thank you.
We have time for a question. Mark?
Can you say a bit more about your tau IR, how it's computed?
I don't know if Danielle wants to go into the details. It's the same that it's been for like the last 2 years of talks. The tau IR.
How's your tau IR computed? Where's it coming from?
Okay, so the tau IR is depends on the optical bit.
Okay, optical depth using what opacity for the dust? Okay.
So that's what it happened in high sensitivity. So the tau internet. So I know what the estimate.
Okay.
Okay, let's thank Kenza again. Okay, so for our last speaker of this session before coffee, we have Coral Wheeler, who's going to go and talk about simulating dwarf galaxies. So from examining to simulating. We were also simulating the other ones. Thank you, Kenza. I'll give 3 minutes.
Awesome, thanks. Great. Yes, I'm very excited to be here. I'm Coral Wheeler. I'm a grad student at UC Irvine. I'm happy to be here to talk about simulating ultra-faint satellites of local group dwarfs. I always like coming to Santa Cruz. I think the level of the science here has been absolutely phenomenal. But I also like coming, because I have a lot of friends here, and sometimes we like to hang out. So last night at the Red Room, some of my fellow conference attendees actually thought that they'd have a little bit of fun with me by challenging me to say some pretty weird stuff during my talk today. I think things like legendary, sababa, and moist earlobe. But I'd have to be absolutely insane or a tenured professor to say something as strange as moist earlobe in a conference talk. So instead of that game, I'm going to celebrate something else I love about Santa Cruz, which is the Shakespeare. James was nice enough to treat us to Macbeth on Wednesday. So I've hidden a few Macbeth quotes in the talk. I've tried to make them relevant to the slides so you can all silently judge me and how well I did that. Okay, so taking the words off the screen, we can see one of the fundamental predictions of lambda CDM, which is the existence of substructure. So this is a very nice dark matter image from the Elvis suite, and you can see that in addition to the dark matter halos we expect to host the Milky Way and Andromeda, lambda CDM predicts hundreds and in fact thousands of smaller subhalos orbiting in and around them. Now it's well known that the situation is much different when we look out into the observed sky. There are currently only about 30 or so confirmed Milky Way satellite galaxies. Even if most of the new DES candidates turn out to be galaxies, we're still talking on the order of tens of satellites, instead of the potentially hundreds and even thousands of potential sites for forming those galaxies. Now, of course, we're not in too much trouble because it's expected that the lowest mass dark matter subhalos will never have formed satellite galaxies, right? Probably having their gas heated away or evaporated by reionization of the local universe. But what is still unknown is at what mass scale that occurs. We still don't know below what halo mass we might expect all halos to be dark. Now, one potential clue to help answer this question comes in the form of this plot, which was already shown by Andreas earlier today. In 2008, Louis Strigari showed that local group dwarf toroidals over a large range in luminosity are consistent with occupying dark matter halos of strikingly similar mass, just a few times 10 to the 9. Well, I would say one and possibly the most obvious way to interpret this is, that's it, we're done. That's the cutoff mass. We're not going to find any galaxies living in dark matter halos below this critical mass. In 2010, James Bullock had a different idea. James suggested that perhaps the common mass scale for local group dwarf toroidals is nothing more than a selection effect. If dwarf toroidals of the same velocity dispersion as existing ones live in lower mass dark matter halos, they would have larger half-light radii, lower surface brightnesses. Now, James very cleverly called these things stealth galaxies, and if they exist, there could be hundreds and in fact thousands of them lying just beyond current detection limits. Okay, so in order to figure out the answer to this question, I wanted to run simulations, very high-resolution simulations. If we're trying to see if tiny galaxies form in tiny halos, we need extremely high resolution. So the best way to do that is with dwarf galaxies, right? Doing that at the Milky Way scale is still computationally prohibitive. So we use the Gizmo code with the sophisticated feedback in realistic environments prescription. This is just some eye candy, one of our dwarfs forming, while I tell you about our details. So I said high resolution. Let me just draw your attention. Yes, just a few parsecs and only a few hundred solar masses. So this is very high resolution. Unfortunately, of course, as Joel told us earlier, the trade-off for that is we can't run a million of these things. We were able to run 4 different sets of initial conditions. 2 dwarfs at 10 to the 10 solar masses in dark matter. This is something we would expect to host about a galaxy of about 1 million solar masses. We ran 2 what we called ultra-faints at just a few times 10 to the 9 solar masses. Now this is low enough that we weren't exactly sure what to expect. One of our 10 to the 10, or more massive dwarfs, we ran 3 different times. Identical initial conditions, just making minor changes to the subgrid implementation. Maybe I shouldn't walk around. All right, so here are our runs. This is just the dark matter distribution. You can see the 2 ultra-faints in the upper right-hand corner. There's common mass scale between the panels. These lower panels are the the identical initial conditions. And this is just dark matter though, right? I ran hydrosims because we wanted to see if any of these subhalos form galaxies. So I'm going to go ahead and overlay the stellar distribution from the simulations in color. Okay, well here's where you should all be extremely excited, because in addition to the centrals that we expected to form massive galaxies, you see we're getting galaxies, tiny galaxies forming in our two isolated ultrafaints, and even more exciting, between 1 and 2 of the highest mass subhalos are forming their own tiny galaxies. How tiny are they? I'm sure you're asking yourselves. So here there's where they sit on the stellar mass, halo mass relation. Different colors, just different runs, so you can see the centrals are circles and their satellites are triangles. And they lie over a couple orders of magnitude in stellar mass. These objects lie just offset from an extrapolated abundance matching from Shea's 2014 paper. But I don't think that's really the important thing. The important thing to notice is that we're forming galaxies in below this critical halo mass of just a few times 10 to the 9.
What is M halo satellite?
It's the peak virial mass. So just a few thousand solar masses forming in dark matter halos as low as 10 to the 8.5 peak. So we don't see a break. To the resolution limit of our simulation, we don't see a halo mass below which everything is dark. We do see a different kind of break that happens to occur at about this same mass. And that is a break in the age of the stellar populations. If we split our objects into ultrafaints below this critical halo mass and more massive dwarfs above this critical mass, we can plot their cumulative star formation histories and see something interesting. Okay, here's that same plot on the left, and I've shown this is the cumulative star formation history for the ultrafaints in cyan and for the more massive objects in magenta. You can see that 100% of our ultrafaints form all of their stars before redshift of 2, and almost all of them form 90% of their stars by the end of reionization, highlighted by this yellow band. Now, this is satellites and centrals, and for the satellites, this is occurring gigayears before they fall into their hosts, suggesting that these objects are being shut down, not by infall, but by reionization-related quenching. So we made a prediction in the paper that below, for objects that form in halos below this critical mass, they will have uniformly ancient stellar populations. That's independently from whether they're satellites or centrals. Oh, and I'd just like to point out, this is also seen for ultrafaints, Tom Brown's work. Okay, so we made some pretty bold predictions with these simulations here that these ultrafaint galaxies should exist around local group dwarfs. But that doesn't it doesn't matter what you predict if it can't be tested. So can we even detect these things? Here is mass-size relation, where I've put confirmed dwarfs as open circles. The DES year 1 results here in black, and I've just put the year 2 candidates here. This is 30 magnitudes per square arc second, so that's Sloan detection limits. If we put our data points on here from the simulations, we can see, okay, well, here are the massive ones. We expected them to be observable. But with the exception of this guy, every single ultrafaint that forms in our simulations does lie just beyond this limit. So, these are simulations, but as we suspected, they are, because they're forming in lower mass dark matter halos, they have lower surface brightnesses, and they lie just beyond what would be current detection limits of Sloan. And what that means is, if I were giving this talk just a year maybe ago, we would all be weeping silently to ourselves because we would have no chance of ever detecting these things. But we live in a very exciting time where new surveys such as LSST and DES are out there doing good work, finding low surface brightness galaxies. DES is already doing it. I expect that we'll be seeing many more of these guys from DES. And in the paper, we particularly highlighted the Phoenix dwarf galaxy, happens to be in the DES footprint, as a very excellent candidate to host its own ultra-faint satellite galaxy. Now, according to the ELVA simulations, there's only about a 35% chance that Phoenix will have an ultra-faint. But it's really important to remember that if you're looking for ultra-faints and you point your telescope at a known local group dwarf, you still have all the volume in between you and the dwarf, right? So if you factor that in, turns out there's a 50 to 65% chance that there's an ultrafaint somewhere in the Phoenix field. Now, it's not just Phoenix, right? Cetus, Tucana, Leo, any galaxy that's about the stellar mass or greater could potentially have one or several of these ultrafaints. And we're working with several people, actually, to look for this. Okay, in conclusion, if you want more details, you can check out the recent paper. Basically, we made a few predictions. Ultrafaint galaxies of a few thousand solar masses should exist as satellites of known local group dwarfs. These ultrafaints and ultrafaint isolated ultrafaint galaxies should have uniformly ancient stellar populations, having had their star formation shut down by reionization. In general, the 50 kiloparsec or so extended region around known local group dwarfs is an excellent place to search for ultrafaints, and not just ultrafaints. A recent paper came out that you can check out where they found a more massive dwarf, but a 10 to the 6 solar mass dwarf as a satellite of an isolated dwarf galaxy, NGC 3109. So even more exciting, they potentially found several ultrafaints that could be satellites of this exact same system. They have to be confirmed with HST. So I really think that this is the tip of the iceberg. I think we're going to be seeing a lot more of these objects. And although we'll have to wait for it, it's observations like these that could have potentially legendary implications for Lambda CDM. Thanks.
Okay, Coral ended early. We have plenty of time for questions. Frank first.
This is very impressive. I'm very impressed that you get these stellar ages correct and everything, and the ultrafaint. This is, yeah. I'm puzzled how it works, but it works. It's beautiful. One thing, have you looked into the dwarf galaxies in the Milky Way and see whether they undergo quenching after they actually come into the Milky Way? Do the simulations predict something that particularly quenches them once they fall in? Not the ultrafaints, but the more massive ones.
For the higher mass?
We always hear about satellite quenching.
Yeah. Well, those objects are almost all quenched, and they all fell in relatively recently. So I think as Sean Fillingham was talking about, it's likely ramp pressure or some fast-acting quenching mechanism.
But they were quenched before they fell in already?
Oh.
Or what quenched them?
Oh, it depends on, okay, but you said for higher stellar mass.
Yeah,
Then I think they were quenched by infall. Ultrafaint should be quenched by reionization, higher mass by infall. Oh, I see. So our simulations are just isolated dwarfs. We haven't yet thrown any of these into a Milky Way hot gas halo, but I mean, we don't have the resolution to.
You had a bunch of centrals, and then you had a bunch of satellites around the central.
I see what you're saying. You're saying if the centrals were 10 to the 6, so the centrals were dwarfs. Yeah.
Sorry.
That's right.
So you just repeated it. The ultrafaint seems to be sensitive to the reionization. But I think since you're modeling the Milky Way environment, you have an additional degree of freedom, which is that you can consider local reionization scenarios. And I guess in your model, you just assume homogeneous.
Yeah.
But one thing you can try actually is to play with the reionization redshift. Maybe, I mean, there are some papers with some ideas about what would be the local reionization redshift for the Milky Way. And actually, it's not the mean reionization redshift. It's more like higher. It will be interesting to see how sensitive your results are to playing with this reionization redshift.
Yeah, I suspect they'll be very sensitive. And Oliver Elbert actually is heading up a project where we're going to run a bunch of these higher, mostly lower mass, and turn off reionization, change the redshift to reionization. So yeah, those results will be forthcoming. But I suspect it'll actually have quite a big impact.
Hi, yeah, so these are really nice simulations, and Roman took my first question, so my second one's going to be, was self-shielding included in these simulations, and if so, how was it done?
I mean, there is self-shielding, but it's not put in by hand. It's just once you get high enough resolution, you'll get some amount of self-shielding.
In terms of the UV background, do you have a density threshold where you just shut off the UV background, or are you propagating that in every cell regardless?
I'm sorry, no, I mean, it's a uniform background, but there's gas in the simulations which is shielding the other gas from being hit by reionizing background.
Yeah, it's done sort of in subgrid, it's done sort of analytically. It's not done 100%.
it's likely more in the cooling function rather than like an actual radiation transfer.
It's definitely not radiation.
Yeah.
But yeah, I mean, we know it's happening. They're not all being uniformly shut down right at reionization. We're having a lot of ultrafaints continue to form stars for a few gig years after.
All right, great. Thanks, Coral, again.
Thank you.
So I hope coffee's out there. I trust coffee's out there. Let's